Yeah, so he just like got yesterday, so
yeah.
and then unselect this.
Okay.
Yesterday.
I have some quizzes that I have graded. You have quizzes that you have graded?
Yeah, I was gonna grade Thursday in class.
Oh, okay. So just swap with somebody.
Okay.
I can start grading next. Also, I have exam.
Perfect.
It's a lot of work, so but I have the keys and I need to.
Yeah.
Well, we were thinking, do you have to run off?
No, no. We were thinking that we could just meet up as TAs and like go through all of them, and so that
All at one time, you mean?
yeah.
Okay. There you go. There are a few more that are coming, and we had some quarantines and some ER visits and some
like on a hill next to a
challenges.
and she just put it right in this here.
Good afternoon, everyone. Let's get underway. Welcome. Let's begin with prayer. And is there a volunteer? Please.
Our dear, kind and gracious Heavenly Father, we're so grateful for the opportunity we have to learn some more biochem and to focus on amino acids and continue with carbohydrates. We're so thankful for all that Dr. Graves has taught us, and please bless us that the Spirit will be with us as we continue to learn, and that we'll be able to improve how we learn as we go throughout this semester. We love you so very much. We say these things humbly in the name of Jesus Christ. Amen.
Amen. Thank you very much. I have had people ask me about the exam and when it will be graded. To be very honest, if it were to be graded by a week from Monday, it would be something of a miracle. But that would be our goal, to try to get it by then. We still have quiz 2 that's being graded, so there's a lot on people's plates right now. Are there questions? Do you have issues, questions, concerns at this point? If you want to raise content, administration, things of that nature. I do have this handout on immunoassays. We'll distribute it. This same document is posted on Learning Suite. My guess is that most of you have had a chance to look at it. But it describes a little bit about the biology of antibodies and beta lymphocytes and describes briefly different types of assays that utilize antibodies that are immunoassays. The only one that you will be responsible for, and I mentioned this last time, is the one that is described in the book, which is a very simplistic ELISA assay. There are other formats and other approaches that are described on this handout, You will not need to know those for the exam, but you are welcome to look at those to gain insight as to how these assays are conducted. All right. We're going to pick up where we left off. We had talked last time about a couple things. One was the concept of a reducing versus non-reducing sugar. You recall that in the formation, as you cyclize the sugar, in the formation of the ring, you will form either a hemiacetal if you're cyclizing an aldose, or a hemiketal if you are cyclizing a ketose. And those are considered reducing sugars because they can open and undergo oxidation in the presence of transition metals. So those are considered reducing sugars. If you modify the hydroxyl group that is formed as the ring is closed, the hydroxyl group on the anomeric carbon, carbon 1 for an aldose, carbon 2 for a ketose, if you modify that, remove the hydrogen and replace it with any other atom, so a carbon or a nitrogen, that makes that bond more stable. So if the hemiacetal becomes an acetal, the hemiketal becomes a ketal. Those do not open. Consequently, they do not undergo oxidation in the presence of transition metals and are considered non-reducing. Okay, this becomes important when we're talking about naming disaccharides, because there is sort of a, if you will, sort of a set of instructions as to how to do this, and it relies on your ability to identify what sugar is non-reducing and what sugar is reducing. Okay, so we're going to start with that. So I'm going to use the board. I'm just going to generate a hypothetical disaccharide. So let me begin. So I'm going to construct one that looks as follows. You'll notice that I'm not indicating hydrogens just for the sake of time, convenience. So this is going to be coupled to a second sugar through what is called a glycosidic bond or a glycosidic link. This would have to be constructed or have to be produced via an enzymatic step. This doesn't happen spontaneously. Okay, so I have now just put together two sugars. I've linked them through a particular condensation of the one carbon of this sugar and the fourth at the fourth carbon of this. This now, notice this was a hydroxyl group. I have now replaced the hydrogen with a carbon. So this is an acetal, this O, carbon O. And over here, we still have the intact hydroxyl group that is formed with the closure of the ring of this particular sugar. So this would be a hemiacetal. Consequently, this is considered to be a reducing sugar. This, as an acetal, is more stable. The ring does not open and close. Hence, this is a non-reducing sugar. And we're going to begin with the non-reducing sugar. So that is the convention. You start in naming this, you start with the non-reducing sugar. First of all, as writing this, I'm going to specify the anomeric orientation. You'll recall that if you're using a Hayworth projection and the hydroxyl is oriented down, that is the alpha anomer, whereas if the hydroxyl group is oriented up, it is the beta anomer. So this then is alpha. All of these will be D, but this indicates the stereochemistry of the next to last carbon, the last chiral center. And now I need to indicate what sugar this is, and I do so with an abbreviated name. If you look at this closely, you probably haven't learned these names yet, but this is galactose. So I'm going to put galactose. Okay, that's going to indicate the actual sugar involved. Now I'm going to specify the ring. You recall that a 6-membered ring was a pyranose because it contains a paran ring. If you have 5 members in your ring, that is a furan, and so it's called a furanose. So this is galactopyrano. And now I'm going to indicate, just in this convention, this is going to be considered a modifier of this particular sugar. Consequently, I'm going to add this SYL, so methyl, benzyl, so forth. Those are an indication that that particular group is modifying some other molecule. Okay, so alpha D-galactopyranosyl, and now I specify the linkage. I'm going from carbon 1 here, 1, 2, 3, 4, 5, 6, to carbon 4 over here. And so that is just placed in parentheses. That indicates the connections between the 2 sugars. And now I proceed to do this same process for the reducing end of my disaccharide. So as mentioned, if the hydroxyl group is oriented up, it's the beta D. And in this case, I have chosen mannose. So mannopyran, and then I'm going to end this with ose. So ose is a common ending for sugars, glucose, mannose, so on and so forth. But the use of OSE indicates that this particular sugar is a reducing sugar. So that is part of the convention. Okay. Any questions about this? Yes?
What is the SYL? What is that?
It means that this sugar is a modifier of this. Okay? I mean, that's what it's meant to indicate. Yes?
So if it were like a ribose that it were connected to, then it would have the cell? Or
if it were ribose, it would be ribofuranosyl. If this were still if ribose were the non-reducing sugar, it would still be indicated by SYL.
So SYL just means that it's.
So in this convention, you consider the non-reducing sugar to be a chemical modifier of the reducing sugar, a substituent on that ring. Okay? I mean, in reality, they're both equally big, so you might argue the point, but that's what this represents. Yes?
So if there was another sugar connected to the mannose, would it be mannopyranosyl and then the next thing?
In general, we don't. This convention is not used beyond 2 sugars. Okay, so be thankful. Yes,
Am I remembering right that you said in this class we only deal with B?
yes, yes. Right. Okay, let's do another one that's a little bit more, well, a little different, okay? So let me remove this. Okay. I'm going to draw now sucrose. Sucrose, as mentioned, is table sugar. It's what we buy at the store and sprinkle on our cereal, whatever, okay? And it is a copy of glucose coupled to a copy of fructose. Needs to match it here. So there's something kind of unique about this in that, in this case, the anomeric carbon with the, which starts off with a hydroxyl here after ring closure, is coupled to the anomeric carbon of the fructose. In other words, we don't have a free hydroxyl on either the glucose or the fructose. And in fact, we have two non-reducing sugars. Neither of these can open. Here we have a ketal, here we have an acetal linkage, and as a consequence, those rings will not open and these sugars cannot undergo oxidation in the presence of transition metals. So then the question is, if the convention is to start with the non-reducing sugar, where do you start here? And the answer is, it does not matter, as long as you're self-consistent. So we can start with the glucose. Again, we start by indicating the anomeric orientation. So this is alpha, so we have alpha D leucopyrano, oops, wrong man, pyranosyl. Okay, we still have to choose one as at least hypothetically modifying the other. So this now becomes a modifier of the sugar if I start with it. Then I indicate the linkage. Here we have 1 for the glucose, but it's 2 for the ketose, the fructose. And now I write out the information about our fructose. So this is, it's a little hard to see, but this hydroxyl group is up for the fructose. So this is beta D fructo, and this is a furan, O, and now this is where things differ. If we had a reducing sugar, we ended with OSE, but if we don't, we end with IDE. So alpha D glucopyranosyl 1,2 beta D fructofuranoside, okay, as opposed to furanose. So this is a little different. There are some examples in the book. I do caution you The artists take liberty in flipping things up and around so they can all of the sugars can fit on the line instead of being stacked. This can be very confusing if you're trying to understand how things are connected or what sugar it is. So the slides, the book, make use of this technique. Okay, questions about naming disaccharides. This is really all we're going to, you can expect probably one problem on the exam, either where you write the name or you draw the structure from a given name. Yes?
What was the orientation for the beta on the fructose again?
So it's the hydroxyl group formed with ring closure,
But it's just going out.
but it's going up, which places it in the beta orientation, at least in the Haworth projection.
Dr. Graves,
Yeah.
what did the furanoside suffix indicate as opposed to just the fructose ending?
It indicates that it is a non-reducing sugar. In fact, it indicates that both are non-reducing sugars. Okay, we're going to now move to some slides, and if I can do this. Maybe. There we go. Okay. So these rules are summarized on this slide. As mentioned, there's an example or two of using this sort of systematic way of naming things. So here on this slide, you can see that this is the common name for this disaccharide is maltose. But you can write this using this more thorough explanation of what you're working with and the connections between sugars using this disaccharide naming convention. Yeah. The which? Oh, on the board? People can't see it anymore, but you can go back to it. 1, 2, 3, 4, 6. 1, 2, 3, 4, 5, 6. Okay, so let me go back. Ditch this for a second. Oops. Okay, so I have labeled, so this is the one carbon. Remember with a ketose, you have the carbonyl is on the 2 carbon. So that is here. This is what was attacked by this 5-hydroxyl group to close the ring. This produces this hydroxyl group. So 1, 2, 3, 4, 5, and 6 for our fructose. Glucose, we've seen before, but there's the numbering for it. As mentioned, they do have some other examples somewhat here, but you'll notice that they have inverted and rotated these sugars so that they all fit nicely on a line, but it makes it very hard to follow. But here are 3 more systematic names for common disaccharides that occur naturally. All right, we are going to talk now about some biological polymers of glucose. Some of these are storage forms of glucose that are intended, they're stored by a particular organism for later use. But we'll also talk about another one that is structural in nature, cellulose, which is the sort of woody, the fibrous component of plants. And we'll spend a little bit of time talking about these. So storage forms of glucose in the human, it is glycogen. This is stored in skeletal muscle. It is stored in liver. The concentration per gram of tissue is substantially higher in the liver, but given that you have a great deal more of the skeletal muscle, overall there's more glycogen stored in skeletal muscle, or can be, than in the liver. Both of these then are ways of putting aside glucose for later times of need. Okay. The other storage form is starch. This is found in plants. So you think of tuberous plants, potatoes, other roots often are full or have a great deal of starch present in them. The starch is made up of two different types of polymers. One is called amylose. It is unbranched. And there's a second one, amylopectin, which is branched. And we'll talk about that as we go along. Glycogen is also branched. And there's reason for doing this. So all of these are alpha-1,4 linked. So we're talking about multiple copies of glucose in its alpha anomeric form, and we're coupling the hydroxyl group of 1 to the 4, or condensing the hydroxyl group of 1 to the 4-hydroxyl group of another copy of glucose, forming the glycosidic link. It turns out that amylose, because of just the hydroxyl groups and so forth, will orient itself something in a loose spiral. This is not an alpha helix. There are no firm dimensions for this, but nevertheless, if you have a long unbroken polymer of amylose, it tends to form this spiraling system. Amylopectin now is going to introduce branch points, and these branch points are found on the 6-carbon hydroxyl group. So let me just walk you through this. So amylopectin and glycogen have these branches. So we have the main chain down here. So going, if you can imagine this, going on for many more copies of glucose, and they are all linked alpha-1,4. So here's the beginning. This is the 1 carbon of 1 copy of glucose, and it's coupled now to the 4 carbon of the 2nd copy of glucose. And so they're kind of end to end, these copies of glucose, and this forms then the main chain of the amylopectin or glycogen. And then notice up here on this 6-hydroxyl group, we introduce another polymer. So we have this branch point, which is alpha-1,6, and then we have another polymer of glucose molecules coupled alpha-1,4. And with a certain frequency, you will see additional branches introduced into the amylopectin and the glycogen. For amylopectin, the branch points are about every 24 to 30 glucose molecules. In other words, you'll have a continuous strand of glucose molecules coupled 1,4, and then after 24 to 25, 26 glucoses, you will have a branch, and then that will extend on and you'll form additional branches. With glycogen, the branching is more frequent. It's about every 8 to 12 glucoses, you will introduce one of these branches. And you have branches on the branches. And in the end, this looks a little bit like a pine cone or a porcupine or something like that, where you really have a spherical particle. You have a central glucose, but then you have all of these branches coming off, branches on branches, until you have many, many termini of these glucose polymers on the periphery, on the outside of this. When glucose is mobilized, that is when you run out of, when you have exhausted your dietary glucose, the glucose in your circulation, then you tap into glycogen. And so by having these many non-reducing ends, these many termini, you can actually mobilize glucose from many sites on a single glycogen particle. So it very efficiently can release glucose to resupply blood glucose levels. So just to put this into perspective, if you, let's say, are a distance runner, let's say you start your run in the morning before you've had much to eat, so you don't cramp up, or and after probably as little as 15 to 20 minutes, you have exhausted the glucose in the circulation. And now you begin to mobilize glucose from glycogen stores. These are local sometimes. So the glycogen in the skeletal muscle can be utilized. The glycogen in the liver likewise will be broken down and the glucose released into the circulation. This will keep you going for another substantial period of time. And when you have exhausted the glycogen, this is turned hitting the wall. It happens at about 20 miles, 20 to 22 miles, and you feel like you're going to die. And it's actually close to the truth. So you've really placed yourself in a hypoglycemic state that is sufficiently severe that you're really having profound symptoms of the hypoglycemia. Now, trained runners who do this all the time, the Kenyans and the Ethiopians and so forth, these amazing people who can run and run and run and seemingly never get tired, they have adapted to this situation. So they are able to keep going, and they don't experience the same sensation that an amateur runner does at 20 to 20 miles. Yes?
I've also heard of like runner's high.
Yes.
Does that have to do with glycogen as well? Like
No, that has to do with endorphins. So these are these these sort of internally made opiates, you know, sort of, and so they are produced, especially I think in trained athletes who do this, and they do provide a sense of well-being as a person is running. Yes.
So I've heard like people say like they have to get over the wall or push through it, and then they feel better afterwards. What happens in that situation?
I think it's the endorphins numbing their pain. It's interesting. There was a publication in the New England Journal many years ago where they actually tested high-performance distant runners at the end of the Boston Marathon. So they sampled their blood, and they actually made a determination of what their glucose levels were. And they were at, so we haven't really discussed glucose levels, but a normal fasting glucose would be about 80 milligrams per deciliter. You begin to experience hypoglycemic symptoms at maybe 60 milligrams per deciliter on down to 40, depends a little bit on the person and sort of their glycogen. Anyway, but certainly by the time you reach 40 milligrams per deciliter, almost everyone feels some of these symptoms. at a threshold of about 25 milligrams per deciliter, you begin to have these neurologic symptoms where you no longer can speak coherently. You become faint, and you pass out, you go into a coma, you die. So that's at about 25 milligrams per deciliter. When they measured these long distance runners, their blood glucose levels were averaged about 25 milligrams per deciliter. So they were literally on the point of coma and didn't know. Okay, so anyway, okay, that's an aside. All right, so these then are the storage forms of glucose. They are intended, they're created to have a reserve of glucose stored in the body for us in the liver, in the skeletal muscle, that is drawn upon as we don't eat. So as part of an overnight fast, you eat dinner and snack a bit and so forth, but at some point you go to bed and then you typically don't eat till whatever, 7 in the morning, or maybe it's noon by the time you actually get to eat something. What's keeping you going is glycogen, okay? So just put it in perspective. All right. I want to talk now about cellulose. And cellulose is this structural polymer of glucose. It is the woody part of plants, the fibrous part of plants, and it differs. Now, it is, in fact, just a polymer that is made exclusively of glucose. However, the linkages are beta 1,4 as opposed to alpha 1,4. And this has consequences. One of the consequences is that our bodies do not have enzymes that allow for the breakdown of cellulose. So if we eat a twig or a matchstick, or we eat the toothpick, we're unable to digest it. It will simply pass through the system. There is a certain amount of cellulose that we encounter in food. We refer to this as fiber. And again, our body really doesn't have the ability to digest the fiber, but that fiber moves down into the large intestine, and there it is acted on by bacteria. And these bacteria are able to break down the cellulose. They utilize this for nutrition, for their nutrition. In the process, they release gas, and this fiber and also brings with it water. Okay, so all of these hydroxyl groups on these sugars interact favorably, hydrogen bond with water molecules, and carry those along with them. Consequently, if you eat a lot of fiber, you have much looser stools. If you eat an extraordinary amount of fiber, let's say you eat that whole pound of cherries, they taste great, but you experience something rather remarkable a few hours later in the middle of the night. So it's important to get fiber in your diet for gut motility. That is, to keep things moving along. Those people who don't have fiber in the diet are much more susceptible to colon cancer and other digestive problems because of this absence of fiber. Okay, so cellulose is unbranched. It is beta 1,4. And it turns out that the sugars are actually rotated, if you will, one versus the other. And this allows for the polymers to be rather linear in nature. Remember, amylose kind of spiral. But in this case, because of hydrogen bonding, as you can see depicted here, we hold these the sequential glucose molecules in a rather straight orientation. Not only do you have hydrogen bonding within a strand of glucose molecules, you also have hydrogen bonding between strands. And this allows for additional mechanical strength to be added to these fibers. If you look at this podium, and for those of you who are far away, you'll have to imagine this, but think of wood. It has a grain to it. This represents the orientation of those cellulose fibers. And if it's a tight grain, it means that those cellulose fibers are very parallel, very close together, and able to substantially hydrogen bond. Now, there are other elements in the wood that give it structural strength as well, but the cellulose really is bearing a lot of this weight. Yes?
I feel like in celery where it's just like straight.
Yeah, straight down, yeah. Yeah, plant stalks. I mean, you think about it, it's rather remarkable. You think of something like a giant redwood down in California. They can be over 200 feet high, and all of that weight is borne, if you will, by these collections of sugar molecules. So when organized in this fashion with very parallel, very closely aligned strands of cellulose, hydrogen bonding, they can be quite strong and bear a great deal of weight. Okay, any questions about cellulose? Yes?
Just trying to understand the slides. It says cross strand or strand that.
So if you, the strands actually go this direction, and this is another copy of cellulose down here. And what you're seeing is these parallel strands are hydrogen bonding across strands, but there is hydrogen bonding within strands. So it is a combination of both. Okay, we're going to move on and talk about one final thing today, and we may not finish, but we will get it started. And this represents now some sugars, some carbohydrates that have very specialized function. So up to this point, we've talked about sugars in the diet. We've talked about storage forms of sugar that are intended to be used as a source of energy later as needed. We've talked about cellulose, but now we're going to talk about these glycosaminoglycans, sometimes abbreviated GAG, GAGs. And these are polymers of disaccharides. These disaccharides are sort of if you will, a reproduced subunit that is linked together again and again and again in a copy of the glycosaminoglycan. So you have this sort of irreducible disaccharide subunit, and those then are coupled together to form the polymer. And these have very, very special functions. Let's look at one of these. This is hyaluronic acid or hyaluronate. It is, let's walk through this. We see something here. It's a little bit hard to recognize. So we have here on the right, we have a glucose molecule that has been modified. The 2-hydroxyl group has been replaced with an amine. So we have glucosamine, 2-glucosamine, but it has been further modified with this acetyl group. So this is N-acetyl-glucosamine. And then over here on the left, we have the 6-carbon. That hydroxyl group has been modified. It has been oxidized to a carboxylate. So this is an acidic acid. It has a negative charge associated with it. As long as we're in an aqueous solution above a pH of, let's say, 2 or 3, this will be negatively charged. Notice that there are peculiar linkages. Well, the beta-1,4 we saw in cellulose, and this one now is beta-1,3, which is somewhat unique to these glycosaminoglycans, in particular, in this case, hyaluronate. The structural elements, the negative charge, the peculiar linkages, and so forth, give it a certain type of chemistry and structure within the tissues where it occurs. Okay, so one thing that happens is that the negative charge in the hydroxyl groups will attract water. So these will be, if you were to take a powder of hyaluronate, it would absorb enormous amounts of water. I think many times its own weight in water, it would absorb that. And it forms this very viscous but very slimy, slippery material. Okay, so the negative charges now will repel one another. So think of polymers, you know, but the negative charges will repel one another. The water is present surrounding those. These become extraordinary lubricants. So the synovial fluid in our joints is predominantly hyaluronic acid, hyaluronate, polymers. And this keeps those bones from grinding together or cartilage against bone. It lubricates those joints to keep them intact for most people for a long time. Yes, there are people who undergo joint replacement and so forth. It's unfortunate, but most of us will go 50 years, 60 years without needing to do that because of the extraordinary properties of the hyaluronate. The hyaluronate also fills the orbit of the eye. So if you talk about the vitreous humor inside the orbit of the eye, it is hyaluronate. So it has a couple remarkable properties. One, it is it's easy to, it can absorb pressure, it can absorb shock without, and cushions, if you will, the eye, the sort of firmer tissues of the eye to prevent it from rupturing with casual bumping of the eye. Additionally, it is transparent to light, which is remarkable. How many organic compounds are completely, allow for the complete transmission of light through them? Very, very few. So a remarkable property. This is also found between cells. These long polymers get entangled with proteins on the surface of the cell and other fibrous proteins present between cells and form this kind of spongy meshwork that surrounds cells. It's sometimes called ground substance, or extracellular matrix is another term for it. But as you can imagine, it allows for you to compress, push cells together, and the water is pushed out to the side until you get to having negative charge really against negative charge, and then it will push back. So it's very elastic. It can absorb a lot of pressure and force without causing the cells to rupture. The cells actually could be relatively easily ruptured, but if you slap your hands, you don't have massive hemolysis because you've ruptured all your cells and your blood vessels and so forth. So the hyaluronate is providing that cushion between cells. Okay, we're gonna have to leave it here. Okay, let me, are there questions before we look? Yes?
So I'm really curious, what is the glycosaminoglycan and what's the hyaluronate? Like, are they're not the same thing?
Well, the glycosaminoglycans represent this collection of polymers made up. So one of them is hyaluronate. Another one is chondroitin sulfate. Another one is keratan. And so we will go through these next time. So the big category is glycosaminoglycans. Hyaluronate is a representative part of that. Yeah. Okay, let me move this story forward. So I mentioned I had gained access to a National Guard unit, 19th Special Forces. I was going to be in a radio company. I was going to go off and go through basic training before my semester ended at the university. So this was really the first time I was going to spend long periods of time away from home. I'd gone off on a couple overnight trips here and there, but this was going to be months away from home. And it was kind of disorienting. I had been going to church quite faithfully, but as we arrived at Fort Jackson in Columbia, South Carolina, we were placed in this building in this very disorganized company, and there was no real leadership there to explain things. Primarily, we knew what to do and where to go. As the intercom came on and you heard profanity, it usually meant that you needed to go outside and stand in formation, and then someone would come along and march you off to get immunizations or to get a haircut or issue you uniform and duffel bags and so on and so forth. And so that first Sunday came. I had no clue as to whether there were church services or not. But it came and it went, and I was unable to get to church. The following Monday, we were actually then assigned to a training unit, and these were highly organized. So there were a company of 250 trainees, there were 5 platoons, there was a company commander and a first lieutenant and a first sergeant and platoon sergeants and so forth, and it was clear, it was easy to determine who were the leaders and who were not. So at this point, things had changed. But then I was also starting basic training, which was a challenge. Okay, we'll talk about that next time. All right, thank you very much. Have a good weekend, please. Stay healthy.
Work on that.